Hello, in this video we're going to start looking at chapter 21, and specifically we're going to look at interconversions between carboxylic acid derivatives and the relative reactivity of carboxylic acid derivatives towards nucleophilic acyl substitution. And I want to start by talking about what are carboxylic acid derivatives. So this is a carboxylic acid, and it's composed of a carbonyl that has an alkyl group attached to one side and a hydroxy group attached to the other side. And a carboxylic acid derivative would be compounds that, when they undergo hydrolysis, will form carboxylic acid. So a hydrolysis reaction is a reaction with water in which you break a bond. And some carboxylic acid derivatives include acid chlorides, acid anhydrides, esters, amides, and carboxylates. And one I forgot to add here at the time of recording this video is nitrile. So you'll have to look in the book for that. It's basically an alkyl group with a cyano group attached, and that's got a triple bond between a carbon and a nitrogen. All right, so we talked in chapter 20, we had a brief introduction to nucleophilic acyl substitution, but I'm going to go over the general mechanism again here. And what happens is that a nucleophile is going to attack our carboxylic acid derivative at the carbonyl carbon in a nucleophilic addition step, and that makes this tetrahedral intermediate. And then if we have a good enough leaving group for Y, it's going to leave in a nucleophile elimination step. And all of your nucleophilic acyl substitution reactions are going to have these two elementary mechanistic steps. Now, some of them may have an additional step, which is a proton transfer, if the nucleophile has a proton that's attached to it that can come off in the last step. And you'll probably see some of that in some of the mechanisms I'll show in a later video or two or three. Okay, so different carboxylic acid derivatives have different reactivity. I want to talk about a couple reasons why that is. So these are our carboxylic acid derivatives here that we showed on the previous slide. And their reactivity increases from the bottom up to the top. So the least reactive would be the carboxylate, followed by amides. Amides are fairly stable. Then we have esters, and then anhydrides and acid chlorides are fairly reactive. Okay, and one of the reasons we can explain that relative reactivity has to do with the leaving group. And if we look here, as we go from the top to the bottom, we have increasing basicity. Okay, and the more basic a group is, the poorer of a leaving group it is. So chloride is a pretty good leaving group, and as we go down here, we have worse and worse leaving groups. They're not so happy about leaving and having this negative charge on them. Okay, so this is very, very basic. The pKa of its conjugate acid is a pretty weak acid, ammonia. Okay, has a pKa of 36 or 38, whereas the pKa of hydrochloric acid is -7. So that's a very strong acid, which means this is a very weak base. Okay, so that's one way we can explain this reactivity trend. Another way has to do with resonance stabilization of our carboxylic acid derivative. So if we look at the amide, one of our carboxylic acid derivatives that is fairly stable, it has some strong resonance stabilization. So this lone pair on this nitrogen can delocalize, and we have this fairly important resonance contributor here. Now, we could imagine something like that happening with an ester, but this is not as strong of resonance stabilization. And the reason we can think about that is oxygen is more electronegative than nitrogen, so it's not as happy bearing this partial positive charge. Okay, and then we could draw something similar for an anhydride. And similar to the ester, we have this resonance stabilization that's fairly weak because we don't like bearing a partial positive charge on this oxygen. And also, so we're using this lone pair to stabilize the anhydride, and we're kind of sharing that stabilization between going to this side or going to that side. So not only is it weak resonance stabilization, but it's shared between two resonance forms. And I think that's the end. So that concludes this brief video, which took a long time to do in PowerPoint, on relative reactivity of carboxylic acid derivatives. In the next videos, I will probably be on the board back there, drawing mechanisms for interconversions of carboxylic acid derivatives. Thanks for watching.